Section 3.4, equations and graphs as polynomial functions. So today we're going to sketch polynomial functions and define multiplicity of a function. So given the following function, x to the fourth plus x cubed minus 10x squared minus 4x plus 24, we're going to graph this in our calculators and then just determine the x-intercepts. So when we graph this and find the x-intercepts, we get x-intercepts of the following: -3, -2, and a +2. So if we were to factor this function, I'm not going to factor the entire thing, but after we factored it, we get factors of the following. So using synthetic division and working our way through, we get a factored form of the following. So how do our x-intercepts relate to our factors? Well, fairly straightforward. After this is factored, if we make this equation equal to 0, which represents our y value of 0, our x-intercepts would end up to be 2. This would be a -2, a -3, and then a +2 again. So if we are to look at the sketch of our graph from our calculators and sketch this, we know this has x-intercepts at -3, -2, and 2, and taking from our calculators, sketch of this graph is going to look something like this. So when we're sketching polynomial functions, it has a y-intercept at 24, and then this is going to look something like this. Okay, so what you should recognize is that mainly from the factors of our x-intercepts and our x-intercepts, I could rewrite this factor as technically x minus 2 squared, an x plus 2, and an x plus 3. Well, if we look at these x-intercepts, we're going to talk about characteristics of our polynomial functions. And as you can see, at -3, the graph goes through -3. It goes through -2, but it comes to a point at 2 and then comes back up. So it actually doesn't go through 2. It's actually we call this a tangent point to 2. And the important thing that you should notice is that the reason why this does this is because there's actually 2 factors of x minus 2, which gave this binomial a squared value. So that's the reason why this takes this shape at this x-intercept, and these values are just to the exponent of 1. So that's why these values just go through that point. So what this relates to is called the multiplicity of a 0. And so the multiplicity of a 0 is basically the number of times a 0 of a polynomial occurs. The multiplicity of a 0 corresponds to the number of times a factor is repeated in the function. The shape of the graph of a function close to 0 depends on its multiplicity. So if it had a 0 of multiplicity of 1, such as the following function, x plus 2, x minus 1, and x minus 4, these are our x-intercepts, -2, +1, and +4. The graph simply passes through those x-intercepts. So multiplicity of 1 means these exponent values on each factor. These factors are just occurring once in the factored form, so therefore they each have a multiplicity of 1. And therefore the graph is simply going to go through those x-intercepts. 0 of a multiplicity of 2. So what this means is that this x minus 4 factor has occurred twice in the factoring process. And so the shape that takes is the graph is tangent, or just touches the x-axis, but doesn't actually cross through it. So as you can see, this x plus 2 has a multiplicity of 1, so it should have an x-intercept at -2, and it should go through -2. But then here at x equals 4, the graph should just touch that x-intercept and then come back in that same direction. So it's actually not going to go through the graph. And then the last multiplicity that we see is multiplicity of 3. And so this is when a factor occurs 3 times within the factored form. And what we say is we say this takes the shape of a point of inflection. So as you can see, this graph goes up. It crosses through -2, but the shape of the graph changes. It changes from a concave down shape, and then at -2 it changes to a concave up shape. Okay, so we call this a point of inflection, where the shape of the graph is actually changing shape at that multiplicity. So multiplicity of 3 takes the shape of at an inflection point. Multiplicity of 2 hits the graph at is tangent to the x-axis, and multiplicity of 1 actually goes through that graph, keeping its same shape. All right, so a real zero of even multiplicity occurs where the graph of a polynomial function is tangent to the x-axis. A real zero of odd multiplicity occurs where the graph of the polynomial function has a point of inflection on the x-axis. Okay? All right, so let's work through some examples here. So I know we can graph this on our calculator. We can type this function into our calculator and get a sketch, but we want to talk about being able to sketch this graph without a calculator. So some key elements we want to talk about, and this just dives deeper from our investigation that we did yesterday. So first thing you want to talk about is the degree of the polynomial. Okay, so the degree of this polynomial, because this is to the power of 3 and this is to the power of 1, if I were to multiply x cubed times an x to the 1, I would get an x to the 4th. So this tells me that the degree is 4, which technically is, what's more important is that it's an even degree. Okay. Another important fact that we need to consider is always our leading coefficient. And our leading coefficient, if this was all multiplied through, my x to the 4th would then be multiplied by this negative. So I don't care what the actual value of the leading coefficient is. What I'm looking for is whether it's a negative or positive. So because it's a negative and our degree is even, this tells me that, so an even degree, a negative leading coefficient, my graph is going to start in quadrant 3 and it's going to start by increasing. Okay, so that means my graph is going to start somewhere down here and it's going to come up. It's going to start increasing. Okay, so that's like the beginning behavior. And then my end behavior, because it's an even degree and it's a negative, this should end in quadrant 4 with decreasing values. So this is just reiterating things that you should have discovered in the investigation. So let's talk about the zeros and x-intercepts. So because this is in factored form, my x-intercepts are going to occur at x equals 1. And this has a multiplicity of 3. And my other one is x equals 6 with a multiplicity of 1. So what this tells me is it tells me whether I need to come tangent to the x-axis or go through it and the shape that it's going to take as it's going through it. Okay, and then the y-intercept, okay, if I wanted to find the y-intercept of this, well technically this x minus 1 cubed could be written like this. So if I were to expand all this, which you do not have to do, to find your x-intercept, technically what you're doing is you're taking each of these constant values and your coefficient in the front. If you multiply all of these values, that will give you your constant or your y-intercept of the polynomial function. Okay, so I'm taking negative times a negative 1 times a negative 1 times a negative 1 times a negative 6. And that will end up giving me a negative times negative positive times negative negative times a negative positive times a negative 6 is going to be a negative 6. So my y-intercept is going to occur at negative 6. Okay, so then intervals where the function is increasing or decreasing, well, it's going to start off increasing. So from negative infinity to my x-intercept of 1, my graph should be increasing. Between 1 and 6, it should switch from switches from increasing to decreasing, and then from 6 on, because at 6 the graph is just going to go through that x-intercept, the graph should still be decreasing. Okay, so how do I know that? Well, initially, because I know the graph has to start here and end here, it's going to start to increase and then eventually has to decrease. So at some point it has to switch to increasing to decreasing, and mainly I know that because of my x-intercept. So let's just sketch this graph now. So when I sketch this graph, what I'm mainly looking for is highlighting your x and y intercepts, and that the graph is taking an appropriate shape. So the graph should increase through these points. At 1, because it's a multiplicity of 3, the graph is going to change concavity. So the graph is going to go from concave down. At this point, it's going to switch to concave up. And then some point between here and here, the graph is going to have to change to decreasing. So that's how I know this is going to come here. And then this has a multiplicity of 1 here. So it's just going to go through positive 6. I'm just going to put arrows at each end, and that would be the shape of my polynomial function. Excuse me. Okay. The base function at f of x equals x cubed. So how do we talk about transformations with polynomial functions? Pretty much is the same as anything else. So x cubed has been transformed to negative 2 square bracket 3 of x plus 1 all cubed minus 2. So describe the transformations that are occurring. So order of transformations, I'm going to talk about my stretches first. So this has a vertical stretch by a factor of 2. This has a horizontal stretch by a factor of 1/3. There is a reflection in the x-axis. And then this moved 1 unit left, so horizontal translation of 1 left. And then a vertical translation of 2 down.
Brent Rankin to the office, please. Brent Rankin to the office.
Okay, so transform each of the following points, and then we're going to sketch the graph. So these points should occur on your regular function. So let's just highlight them. I'm going to go up by 5s, or just so I can work with these numbers nicely. So this is going to be 10, 20. And then I'm going to exaggerate the numbers this way. So these are going to go up by 1s. Just to exaggerate so I can see the graph a little bit better. So if I were to apply each of these transformations to these graphs, right? So if a negative 2, negative 8. So I'm going to horizontally stretch this by a factor of 1/3. So this would be negative 2/3. I am going to vertically stretch this by a factor of 2. I'm also going to reflect it in the x-axis. So this would become a negative 16, but now I'm going to reflect it, so it becomes a positive 16. This point is going to become a negative 1/3. I'm going to stretch this by 2, it's negative 2, and then flip it, would be positive 2. 0, 0, that's not going to change after our reflection or after our stretches. This point is going to become 1/3, comma, negative 2. This point here is going to become 2/3, comma, negative 16. Okay, so now we're going to translate everything. Okay, so let's translate 1 left and 2 down. So this point is going to become negative 5/3, comma, 14. Negative 4/3, comma, 0. Negative 1, comma, negative 2. Negative 2/3, comma, negative 4. And negative 1/3, comma, negative 18. All right, so if we were to think about sketching this graph, so the sketch of a base cubic function, and if you were to think about your original points at negative 2, the graph should be at negative 8. So I should highlight this, expand this a little bit more. Let me get my eraser here. So originally this point was at negative 2, comma, negative 8, a positive 2, comma, positive 8, and 0, 0. So if I think about, this is kind of an exaggerated graph, if I think about this original function, it looks something like this. Okay, so this is our base function, and now I'm transforming this. Well, technically this point here at negative 2, comma, negative 8 has become negative 5/3, comma, 14. So negative 5/3 is just less than negative 3, and 14 would be right around here. So this point is transformed to this point. Negative 4/3 is just past negative 1, and that point's going to be at 0. Negative 1 and negative 2, so maybe right around here. Negative 2/3 and negative 4, so right around here. And then negative 1/3 and negative 18, right around here. So what's happened is this graph has horizontally been compressed, I guess, by 1/3. So it should be shorter this way, but it's also been stretched vertically. So my new graph should look something like this. Okay. So reflected and stretched both horizontally and vertically. Actually, now that I think about it, this point is off by 1. There, that looks better. All right, and that is the shape of the graph afterwards. Okay? Okay. So polynomial functions with a leading coefficient other than 1. So every polynomial function can be written as a product of its factors and a leading coefficient. Every polynomial has the same number of factors as its degree. The factors may be real or complex. Okay. Excuse me. Okay, example number 3. The graph of a third degree polynomial function p of x is shown. The graph passes through the point 2, negative 24. Write the equation of the function in factored form. So when we look at this, we want to look at how does the graph cross our x-intercepts, right? Thinking about our multiplicity. And then we always are going to assume our c value, that it has some leading coefficient, possibly 1, but potentially other than 1. Okay, so, and then we're going to use our point to find that leading coefficient. So if I were to write the function of this graph, my x-intercepts are at -1, 0, and +3. So I'm going to write my leading coefficient as some letter C. I don't know what that is. It has an x-intercept at -1, so that factor would be x plus 1. It goes through 0, so that factor would just be x. And then my other factor would be an x minus 3, because it has an x-intercept at +3. So now, in order to find or calculate this C value, I can simply substitute this point x and y for x and y in my equation and solve for C. So I'm going to substitute y with a -24, substitute x with a 2, and then we get this value. So 2 plus 1 times 2 times 2 minus 3, this works out to be a -2C. Divide by -2, and my C value works out to be 12. So my factored form would be 12, and then I'm going to write, we tend to always see this factor x in front of my other set of brackets, so that's how I'm going to write it. So my coefficient would be a +12, x plus 1 times an x minus 3. So this would be my equation in factored form. Okay, write the equation of the function in standard form. So standard form means we actually want to expand this entire expression. So to do that, we're just expanding this out. So I'm going to FOIL these values first, or expand them, distributive property. So I get an x squared minus 2x minus 3 when I expand that out. And now I'm going to run my 12x through my set of brackets, and I get a standard form of 12x cubed minus 24x squared minus 36x. All right, moving on to example number 4. Given the polynomial x to the 4th minus 5x squared plus 8x minus 12, we can describe this as a 4th degree polynomial with potentially 4 zeros, or 4 factors. The polynomial can be written in factored form as p of x equals x minus 2 times x plus 3 times an x squared minus x plus 2. This tells us that p of x has 2 real zeros at x equals 2 and x equals -3 and possibly more. The problem is, once it gets down to this factored form, this can no longer be factored further. So how do you find if there are more possible zeros? Okay, you'd have to use the quadratic formula with this quadratic to figure out if there is more. So using our quadratic formula, if I were to solve this, I would get 1 plus or minus the square root of b squared, which is -1, minus 4 times a times c, all divided by 2 times a. So what I end up with is I end up with a negative value inside my radical, which I know this is not possible. Okay? So even though this is a 4th degree polynomial that would potentially have 4 x-intercepts or 4 factors, it doesn't, right? It is only going to have 2 x-intercepts or 2 factors, okay? So therefore, even though it's a 4th degree polynomial, there are only 2 zeros. So 2 x-intercepts. So, as a note, if a real polynomial function has non-real zeros, they will always occur in pairs in the form of p plus or minus root q over r, which is the same as this case, where this q value would be a negative number, so it'd be less than 0. Non-real zeros are also known as imaginary zeros or complex zeros, which we don't talk about or learn in Math 30, but you just have to recognize that it is possible to have a polynomial of fourth degree that won't actually have 4 x-intercepts. It's only going to possibly have 2, and this would be that scenario. This